All right, so this is section 11.6, video number 3. In video 1, we talked about absolute convergence and the ratio test and did a bunch of examples. This one, we're going to do the root test, which is another test for absolute convergence. And the good thing about the root test is the criteria for it are identical to the ratio test. So if you know the criteria, they are the same. The only difference is what you're looking for as far as when to use the root test. But it's really a pretty straightforward test if you know all the other things. And I think we'll be able to get this one done in this one video. So let's get to it. So the root test, again, it's a test for absolute convergence. And what you're looking for is you are looking to see that the series is something where everything is being raised to an nth power. Typically, you're going to have, well, not typically, you need to have some kind of a function of n being raised to the nth power. If you just have a constant being raised to the nth power, well, that's a geometric. Just go geometric and don't worry about this root test. But here you'll have some kind of n's being raised in some fashion to an nth power. There's one special note here, which we'll talk about, where that doesn't have to be the case. But again, criteria is the same as the ratio test. If the limit as n goes to infinity of the nth root of your series is less than 1, it's convergent. Greater than 1, it's going to be divergent, and equals 1 will be inconclusive. So what are we looking for when we get to this? There's one thing that makes it just slightly different, and you just kind of need to know this one. I'm not going to go through a proof of this of any kind, but the limit as n goes to infinity of the nth root of n, or the nth root of n to the first power, is 1. Okay, you kind of need to know that one. So let's put a little asterisk right there. You need to know that one. It will come into play. And the general idea is just remember that if the nth root of something raised to the nth power basically cancel each other out. Okay, and that's kind of why this works out. All right, so our first example. Here we have the series of e to the 2n over n to the n power. Again, come up with a hypothesis. N to the n in the denominator is going to be an iterated function. It should grow much faster than the exponential on the top. Therefore, we would assume this is probably going to be convergent. We just need to show it. What I have are some kind of functions here where I've got these functions being raised to the nth power. The functions are not constant, so we can't use geometric here. But what I can do is I can rewrite the series. Let's rewrite it so that it looks like everything being raised to the nth power. Remember that e to the 2n is the same thing as e squared to the nth power. So we're going to rewrite that as e squared divided by n, all raised to the nth power. Now you should be able to see, oh, okay, everything's being raised to the nth power. Let's use the root test. And the root test says, if we take the limit as n goes to infinity of the nth root of the absolute value of the series, which is going to be the absolute value of e squared over n raised to the nth power. Well, remember that the nth root and the nth power are basically going to cancel each other out, so we're going to end up with the limit as n goes to infinity of the absolute value of e squared over n. E squared is a constant, n is going to grow, therefore this is going to approach 0. 0 is less than 1, and therefore we have a convergent series, just as we hypothesized. All right, so that's what it is for the root test. Let's go ahead and do the rest of these examples. I don't know why there's such a space here. There we go. Determine the convergence or divergence of the series. So again, you can see I've got some kind of a function with n's in it, all raised to the nth power. Root series lends itself perfectly to this one. So it would be the limit as n goes to infinity of the nth root of the absolute value of 1 over n to the nth power, which is the same thing as the limit as n goes to infinity of the absolute value of 1 over n, which goes to 0, which is less than 1. And therefore, this is convergent. And again, you would have expected that because of the fact that you have, technically, if you were to distribute the n, it would have been 1 on top and n to the n on the bottom. It's a constant over an iterated. It's pretty much a no-brainer there. That would be convergent. All right, next example. Something that looks quite a bit more challenging. It looks horrible, but it's not, because I've got this rational function inside the parentheses all being raised to the nth power, which means I can apply the root test. And again, the notation here is very important. Just make sure you're writing it correctly. So this will be the limit of the nth root of the absolute value of the a sub n term to the nth power. Well, again, nth root, nth power go away. So what we get is the limit as n goes to infinity, the absolute value of 6n plus 5n cubed divided by 2n cubed plus 3n squared minus n plus 1. And just be careful, because that numerator was not written in the descending order polynomial, not your standard form. So the dominant term on top is the 5n cubed. The dominant term in the denominator is 2n cubed. Since they are the same, we divide the leading coefficients and we get 5/2 for our limit. 5/2 is greater than 1, and therefore this one would be divergent. All right, moving on. Example number 4. So let's see, I've got a constant over a natural log of n raised to the n. Again, that's iterated in some fashion. Even though it is a natural log, it's still a function of n raised to an n. So let's go ahead and apply the root test. Limit as n goes to infinity, nth root, absolute value, 2 over the natural log of n raised to the n, which is going to become the limit as n goes to infinity of absolute value of 2 over the natural log of n. That definitely approaches 0 as n goes to infinity, which is less than 1, and therefore convergent. Okay, again, the biggest thing here is just recognizing that you can use the root test. Once you do, it's one of the easier tests to use. Okay, so the next one. The next one is a little bit different, because everything has to be raised to the nth power. Well, the numerator n is not being raised to the nth power. I can't just say that it's now n over e to the n, because the n itself is not being raised to the nth power. But this is where that special note comes into play. So we're still going to use the root test, and this is how we're going to do it. We're going to take the limit as n goes to infinity of, if I were to apply the root test, I can separate roots in the numerator and the denominator, which is what we're going to do. So we're going to make this the nth root of n in the numerator, and then the nth root of the absolute value of e to the n in the denominator. Now, if you remember, the note that we had on the previous page said that the limit as n goes to infinity of the nth root of n is 1. So that's the numerator. The denominator, I can still apply the limit and say that the limit as n goes to infinity now of e, well, that's a constant, so it's just going to be e. So what we get is 1 over e. 1 divided by 2.71, blah, 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 is going to be less than 1, which means this is convergent. So again, you can apply the root test as long as you have a singular or solo n that you're going to take the nth root of, because we know that that limit as n goes to infinity will approach 1. All right, example number 6. Let's see, I've got 4n to the n power over 3 to the 2n plus 1 power. Again, everything here is being raised to an n power, so we can apply the root test. You may want to rewrite some of this. As a matter of fact, let's go ahead and do that. I'm going to rewrite this just to make it easier as 4n to the n. There's no problem with that. 3 to the 2n is the same thing as 3 to the 2n plus 1 is the same thing as 3 to the 2n. So this piece right here is the same thing as 3 to the 2n times 3. But 3 to the 2n can also be rewritten as 3 squared to the n, which is the same thing as 9 to the n times 3. So really what I'm going to get here is a 3 times 9 to the n out of that. And then I can actually pull that 3 out to the front because it's not being raised to the n power, it's just a constant. So what we get is 1/3 of the sum, as n goes from 1 to infinity, of 4n to the n over 9 to the n. Now everything there is being raised to the nth power. I can apply the root test. So let's do that. The limit as n goes to infinity, I'm going to take that 1/3 all the way out to the front. Properties of limits, we can do that, of the nth root, the absolute value, 4n over 9 to the nth power, which is going to be 1/3 of the limit as n goes to infinity of the absolute value of 4n over 9. If we plug in infinitely large values, this thing just goes off towards infinity. And infinity is definitely a number which is greater than 1. Therefore, this one is divergent. All right. Moving on. No more on that page. I believe that this is our last example. Yep, it is. So let's determine the convergence or divergence of this series. In order to do this one, everything is being raised to the n. Excuse me, that makes this relatively easy. So we'll take the limit as n goes to infinity of the absolute value, of the nth root, of the absolute value of 2 plus 3 nth root of n, all to the n power. Nth root and nth power go away, and what we get is the limit as n goes to infinity of the absolute value of 2 plus 3 nth root of n. Again, this is where we're going to apply that property or that note that the limit as n goes to infinity of the nth root of n is 1. So ultimately what you get is 2 plus 3 times 1, which is 3, or 5. Okay, 5 is definitely a number bigger than 1, and therefore this would be divergent. Which really should have made sense in the first place because I'm taking some kind of a function there and raising it to an infinitely large, or adding this. There's no fraction there, so really should have made sense that this would have just diverged anyway, but that's showing it. All right, that is the end of the root test and the end of 11.6. That should be plenty enough. Now we're going to put all this stuff together and see why we're using it in the first place.